Welcome to lecture 3. In this lecture, I intend to describe you something about routing. Therefore, after this lecture, I expect you to describe different routing types, describe routing function, and classify different routing protocols. Let's start our today's mission. Cisco internal routing logic. In the previous lecture, we mentioned that routers are responsible for routing. But the question is, how do they do their work? How do they know how to forward the packets or where to forward the packets? The answer is routing table. There is a table inside each router which is called routing table. This table has 5 fields: network, subnet mask, next hop, outgoing interface, and metric. This row is called a route, or each entry in the routing table is called a route. A route implies that if a packet comes to this network with this subnet mask, the next hop or the next router is 10.0.0.1, which is a neighboring router. And if you want to reach this next router, you have to go from this interface, and the metric is 1. Metrics come to calculation when there are 2 similar routes, and if there are 2 similar routes, router choose the route with the least metric. This method or this internal routing logic is called process switching, which was the first method which has been used in Cisco's routers. During the years, Cisco tries to improve the functionality and the speed of the routers, so they invented new methods. The next one, or the next internal routing logic, is called fast switching. In this routing logic, Cisco made 2 improvements. One of them is keeping another list in addition to the routing table, which is listing the specific IP addresses for recently forwarded packets. Furthermore, the router keeps a copy of new data link headers used when forwarding packets to each destination. Therefore, rather than build a new data link header for each packet destined for a particular address, the router saved a little effort by copying the old data link header. So Cisco made a really improvement in routing process. And finally, Cisco introduced Ceph, Cisco Express Forwarding. Ceph, like fast switching, uses additional tables for faster searches and save outgoing data link headers. However, Ceph organizes tables for all routing table destinations in advance, not just for some of the specific destination IP address. Ceph also uses the sophisticated search algorithms and binary tree structures as compared to fast switching. Hence, the Ceph table searches that replaces the routing table searches take even less time than the fast switching method, and it caches the data link headers as well. So as we see that internal routing logic grows during the years, and Cisco tries to improve the router functions. As we saw in the previous slide, routers forward the packets based on the routing tables, and if there is not a route for a specific destinations, routers drop the packets. There are 2 types of routing: static routing and dynamic routing. The difference between the static and dynamic routing is that who is filling this table. In the static routing, network administrators are responsible for filling this table, and they tell the router where to forward the packets. But in dynamic routing, routing protocols are filling this table. Routing protocols are some instructions and algorithms which have the ability to create these routes based on the related information. We will define different routing protocols in the next slides. Each routing protocol, regardless of its type, has to do 4 things. First of all, a routing protocol has to learn. If we call these routers router 1, router 2, and router 3, router 2 has to learn the related information from router 1. These information are different in the various routing protocols. The next duty is advertising or teaching these information. The routing protocol, which is enabled on router 2, has to advertise or teach what it learns from router 1 to router 3. This process is called advertising. If there are 2 or more routes from router 1, for example, to router 3, when router 1 intend to select the route between itself or the network behind it to the router 3 or the network behind the router 3, router 1 has to select one of these routes. Although there are load balancing options in routing protocols, but for now just assume that the routing protocol has to select one of these routes. In this situation, router 1 or the dynamic routing protocol, which is enabled on router 1, select the best route. This is where the metrics comes in. The router 1 select the best route based on the metric. The metrics are different between different routing protocols. We will describe it in the next slides. And finally, if there is something changes in the network, for example, there are 2 routes here and router 1 select this route as the best route, and now this link is down. The dynamic routing protocol has to action now. What? Select the other route and get the network to the normal situation. This process is called convergence, and the time which is needed to converge the network is called convergence time. This is one of the parameters which is important when we are comparing different routing protocols. So each routing protocol has to do 4 things: learning, advertising, selecting the best route, and network convergence. Different routing protocol types. There are 2 methods or ways for classifying routing protocols. In the first method, routing protocols are divided into 2 groups of IGPs and EGPs. Before we describe IGPs or EGPs, we have to define an expression. This expression is AS, or autonomous system. An AS or autonomous system is a part of a network which is owned and managed by a company. In this perspective, routing protocols classified into 2 groups of IGPs and EGPs: interior gateway protocols and exterior gateway protocols. IGPs or interior gateway protocols are routing protocols which do routing inside an AS. So if a routing protocol do routing inside an AS, we name it an IGP. For example, RIP, OSPF, and our course hero EIGRP are IGPs. But an EGP or exterior gateway protocol is a routing protocol which do routing between different AS. In today's world, there is only one EGP, and this is BGP, Border Gateway Protocol. BGP is the routing protocol which is used inside Internet. And as we know that Internet is nothing more than networks of networks. So BGP do routing between different networks which is owned by me, you, and many other persons around the world. In the next perspective, we divide routing protocols into 3 categories: distance vector routing protocols, linked state routing protocols, and advanced distance vector or balanced hybrid routing protocols. Let's compare these protocols. The difference, or the main difference between these categories, is the criteria for selecting the best route, or metric. In distance vector routing protocols like RIP, the best route is the route which has the less routers in between, or we call it hop count. As we mentioned before, hop in routing terminology means router. So hop counts means the number of routers in between. So in the view of a distance vector routing protocol like RIP, the number of routers in the path is the criteria for selecting the best route. For example, if a router sees this path with 2 routers and this path with 3 routers, the routing protocols select this route and do not regard parameters like the bandwidth or other parameters. In link state routing protocols like OSPF or ISIS, intermediate system, the criteria for selecting the best route is cost. This cost comes from parameters like bandwidth. And finally, in advanced distance vector or balanced hybrid, which is our hero, is inside this category, EIGRP is the only routing protocol which sits here. The metric comes from a sophisticated formula which we will discuss it in the next lectures. But for now, I just want you to know that EIGRP is not the distance vector pure and not the link state pure. It's something between these two types. Let's compare these routing protocols in more detail. Among many differences between distance vector and link state routing protocols, I just select some keys. First of all, distance vector routing protocols sends full updates. It means that they sense all of their routing protocol entries when they want to advertise. But in link state routing protocols, only partial updates are sent. Partial updates are changes or only link states. Distance vector routing protocols have slow convergence in comparison to fast convergence of link state routing protocols. Distance vector routing protocols are unaware about network topology, but link state routing protocols maintain a network topology table to know about everything about topology. Distance vector routing protocols are simpler to configure, but link state routing protocols could be harder to configure. Although there are many different algorithms to prevent routing loops in distance vector routing protocols, but they are still susceptible to routing loops. Link state routing protocols are less susceptible to routing loops. And as we saw before, RIP and IGRP are distance vector routing protocols, and OSPF and ISIS are some examples of link state routing protocols. As you could guess, distance vector routing protocols seem to have less performance than link state routing protocols. This is because distance vector routing protocols, at least the first generation of them, are older than link state routing protocols, and these are newer ones, so they are more powerful and many optimizations are applied on them, so they are more powerful than distance vector routing protocols. A question may arise here. Could we configure static and dynamic routing together in a specific router? The answer is yes. But if we configure static and dynamic routing or 2 dynamic routing protocols, what would happen if the static route tells the router for a specific network goes this way and the dynamic routing protocol says that way? What would happen? Which routes would be selected by the router? In these situations, administrative distance is the selection factor. As you could see, each route type has a specific administrative distance cost. The connected routes, which are the directly connected routes based on the IP addresses which is configured on router interfaces, has the topmost priority. After that, static routes have the topmost cost, and BGP external routes, EIGRP internal routes, and other ones in a row. So, for example, if we configure static routing and EIGRP together, routers listen to our network administrator, not EIGRP, and put this route in the routing table. Now it's summary time. In this lecture, first we learned something about routing logics, and we saw that historically there are 3 different methods for routing: process switching, fast switching, and Ceph, and we saw the differences between these 3 methods. Then we saw that there are 2 different routing methods: static routing and dynamic routing. In a static routing, the network administrator is responsible for filling the routing table, but in dynamic routing, routing protocols have this responsibility. After that, we saw the different duties of a routing protocol regardless of its type. Then we classify different routing protocols in two perspectives. In first perspective, routing protocols are classified to IGPs and EGPs. And in the second perspective, routing protocols are classified into distance vector, link state, and advanced distance vector routing protocols. And we saw the key differences between these. And finally, we saw the administrative distance, which is the selection factor when we're configuring two types of routes. I hope this could improve your knowledge, and see you in the next lecture.